Okay, now let's have this introductory statement. If capital X and Y are approximated by small x and small y with corresponding errors, of the x and the y. You have exact, that means that your capital X is the exact value. Let's say you have 2.401, that's the exact value, and you round it off to maybe 2.4. So you have the exact value, which is our capital X. We have the approximate value, which is small x. 2.40 is our exact value. 2.4 will be our approximate value. But by you rounding off or approximating capital X by small x, you've created an error, dx. Then the same applies to y. You have the exact value of y as capital Y. Then you decide to write it as small y. Let's say you have 3.1 and you decide to write it as 3. In that case, the exact value will be 3.1. The approximate value will be the 3. And by you writing it like that, you've created an error, the y. Now, what do they ask you for here? They'll ask you to derive the expressions for the absolute error, for relative error, for percentage error in addition, subtraction, multiplication, and division. When I add x to y, which error am I going to end up generating? Because x has its own error and y has its own error. We've done this, of course, using the values, error bound, those error bound we're looking at. But we're dealing with known values. But in this case, they are giving you unknowns and they want you to derive the expressions. They want you to derive the expression for the absolute error in x plus y. Derive the expression for the absolute error in x times y. Derive the expression for the absolute error in x divided by y, and also in x times y or x minus y, something like that. So in this case, we're going to deal with unknowns, but what we shall be working out is not far different from what we've been looking at. The difference is what we've been looking at, they have been giving us values. They've been giving us values and ask us for the errors. This time around, they're giving us unknowns. They want us to get the corresponding expressions for the errors in the operations of this, maybe by addition, by subtraction, by multiplication, and division. So that's what you're going to do. So you may be asked to derive expressions for the absolute error, expression for absolute error, relative error, and percentage error. Percentage error in addition, subtraction, and subtraction, multiplication, and yeah, so this is what we're going to do. In this section of this topic, this is what we're going to look at basically. We're going to derive different formulae for the errors in division, addition, subtraction, and multiplication. So they're giving you unknowns. They'll give you unknown, one of them representing the exact value, another one representing the approximate value and the corresponding error in it. Then they ask you to derive the expression for the error in addition, subtraction, multiplication, and division. Let's start with addition. Addition. That means we're dealing with x plus y. If I know, for instance, you may measure the length of maybe a rectangle as x, then you measure the width of the rectangle as y. Then they ask you to, of course, if x has its own error, maybe it is subject error, then y is also subject error. They will ask you to find the error that will be there in the perimeter. They may ask you to find the error that will be there in the perimeter of that rectangle due to the errors in length and width. Or you're measuring weights, you're measuring two things. You measure the length of something, then you measure the length of something with errors in them. And then they say, find the error in total length, or derive the expression for the error in total length. Of course, you've seen how you can find the error in addition, error bound in addition, where you find the minimum value, find the maximum value, then subtract the two and divide by 2 to find the error in the sum of those two. But in this case, we're dealing with derivation of expressions. Okay? They're going to ask you to derive the expression for the total error in x plus y. Now here, this is what we do. And this is how we start. Let's be very careful, because now this is the main major concept in error analysis. These are the questions that you're going to find very often in the question bank on error analysis. So here we have the exact values. We're going to use this introductory statement in all addition, subtraction, and everything. So we have the exact values. We have a set of exact values. Our exact values are, we have capital X and capital Y. These ones are representing exact values, because they are saying if X and Y are approximated by this, that means that the capital X and capital Y are the exact values, small x and small y are the approximate values. But always some questions, of course, while teaching, we always teach like that. We use capital X for exact, capital Y for exact, then small for approximate. But when you go for exam, like the hello, mute yourself. When you check out, for those with question banks, when you check out in 2016, they brought the same question, but instead used small letters to represent exact values and used capital letters to represent. Hello, can you mute yourself? We're going to substitute Z, where the Z, we put the approximate value of Z plus the error made in Z, like that. So here we shall have approximate value of Z plus the error made in Z. The whole of this is representing Z, equals to the approximate value of X, which is small x, plus the error made in X, which is dx. That's what we have. Then plus the approximate value of Y plus the error made in Y. That's what we have, like that. So the error made, Z plus the error made in Z will be equivalent to X plus Y plus error made in X plus error made in Y, like that. So then at this point, we can now take Z the other side. We shall end up with error in Z being equivalent to X plus Y minus Z plus error in X plus error in Y. A moment. Okay. Plus error made in Y. But what is Z? X plus Y, if you look at this point here, small z is the same as X plus Y. So where there is Z, you can substitute X plus Y. So you shall end up with error in Z being the same as Z, which is X plus Y, minus Z, which is this other Z, this Z here, which came from this side, then plus error in X plus error in Y, like that. So this and that can cancel, end up with error in Z being equivalent to error in X plus error in Y. Now, by you adding, if you add X to Y, and X has an error of the X, Y has an error of the Y, then for you to get the total error in the sum of the two, the error in X plus Y will be simply the same as the error made in X plus the error made in Y. And I think while doing the other work of error bound in addition, we came up with such a conclusion where we realized that the error in addition, you simply have to add the corresponding errors. So this is what we have. If, for instance, they say you have values x equals to 2.41 and maybe y equals to 3.43, and these values have been rounded off this number of dp's. If they say they have been rounded off, that means that they are subject errors. Now the error made in x will be a half times 10 power negative 2, and the error made in this, let me put here 4. The error made in y will be the same as a half times 10 power negative 3. This will be 0.005. This is the maximum possible error in x. Then here the maximum possible error in y will be 0.0005. Now they can say find the error made in x plus y. Here you simply add them. You add 0.005 plus 0.0005. This gives you 0.0055. That is the error made in the sum of x plus y. That's what the formula is telling us here. That if you're getting the error in z, which z is representing x plus y, the error in x plus y will simply be the same as the error in x plus the error in y. So in the previous section of this topic, we looked at how you can find the error in the sum by finding the maximum value, you find the working value, or you find the minimum value. Then you say the error is either the maximum value minus the minimum value divided by 2. That's what we looked at. Where we said if you want to find the maximum in x plus y, you find x max plus y max. If you want to find the minimum, it will be x min plus y min. Then the error will be maximum value in this minus minimum value in that divided by 2. That's what we're looking at. But in this section, we're doing the same, only that we're deriving. We instead deriving the expressions for the corresponding errors in addition, subtraction, division, and multiplication. So this is what we have. But then we talked about absolute error. This is not absolute error. We defined absolute error as the magnitude of the error. We found the expression for the error in x plus y. But if they ask you to find absolute error, to find the expression for the absolute error, we don't stop here. Because absolute error, we know that must be having the magnitude. We get the magnitude of the error. So if you're looking for the absolute error, then what we do here is we introduce modulus. The error in z must have modulus on it, magnitude. This will be the same as the error in x plus the error in y, modulus. So this gives us absolute error. But then there is another property that you look at in paper 1 in details. I'm just simply going to demonstrate it for you here slightly. Let's have some side work here and I show you something. If you have the modulus of 2 plus 4, the modulus of 2 plus 4, this is the same as, it gives us 6. The answer will be 6. What if I get the modulus of 2 plus the modulus of 4? This also gives me 6, isn't it? It also gives us 6. So this one tells us that it may give us an illusion that if I get the modulus of A plus B, according to what we've just done here, this will be the same as the modulus of A plus the modulus of B. That's what this is telling us. But let's try this with negative values and see if it holds. If it holds for negative values, then it means it is true. This expression, we can use it. But if it doesn't hold for negative values, then we shall call it off. Let's try it with negative 2 plus 4 modulus. What does this give us? Negative 2 plus 4 modulus, what does this give us? Can I have some responses? 2. It gives us 2. Now, what if I have negative 2 modulus plus 4 modulus? What will this give me?
6.
This gives me 6. Now, you see that in case 1, they were equal to each other. This one was equal to the other one. But here, we're getting, if I can write it in general, A modulus plus B, like that, is less than, you see that 2 is less than 6, is less than that. Now, if you combine the two of them, then you can say A, because if you combine case 1 and case 2, A plus B modulus is sometimes equals to and sometimes less than. Sometimes equals to when you're dealing with positive values, and sometimes less than A modulus plus B modulus. So this is our general, the general expression for that. So whenever you have A plus B modulus, this is sometimes equals to or less than modulus of A plus modulus of B. In mathematics, we say A plus B modulus is at most equals to, this is the maximum possible value it can never be. It can never go beyond that. So if they ask you to find maximum absolute error, maximum absolute error, we've seen it from here that this is the maximum possible value. This one can never be. So from here we shall say our dx plus dy, ln x plus ln y is always less or equal to, less or equal to ln x plus ln y modulus. That means if you want to find the maximum possible absolute error in x plus y, you have to add absolute errors in x plus absolute error in y. So here we can now therefore say the error in z, error in addition, is less or equal to x plus that. And this is what they always ask you. There's a marking point. This is a marking point here. When you're changing single modulus to 2, this step is very important. You can't just jump from here to the last step. You always have to show this intermediate step here. That's a marking point. So they'll ask you to derive, the question will be, find the maximum, derive the expression for the maximum possible error in the sum of x plus y, in the sum of x and y. This is the expression for the maximum possible error or the maximum absolute error. So therefore, you can conclude here and say the maximum absolute error, maximum absolute error in approximating x plus y with x plus y is error in x modulus plus error in y modulus. They'll always ask you for that expression. Can I have some questions before we proceed? What we've been doing is we've been looking for the expression of maximum absolute error in the sum of x and y, or in approximating capital X plus capital Y with small x plus small y. We have some questions there before we proceed.
Teacher.
Yes, please.
All this we have done, is it examinable? Like, will they ask for it in a paper?
Yeah, they do. You check. You have a question bank?
Teacher.
You have a question bank with you there?
No, not here, but I have one.
You'll check in the question bank. All those questions are there. It's examinable.
Okay.
Maybe for the sake of answering your question, I can share with you some of the work that I have here to show you that it is examinable. But I'll share with you towards the end. I'll show you those questions. Next is next, after finding the maximum absolute error, they'll ask you to find. So please can you repeat the conclusion? Somebody saying, I repeat the conclusion. So the conclusion is, we are saying the maximum absolute error in approximating x plus y with small x and small y is this. So let's go back to the introduction. The introduction we had here. What's the introduction? They are saying, if capital X and capital Y are approximated by, I'm instead grabbing them, capital X and capital Y are approximated by small x and small y with corresponding errors of the x and the y. You may be asked to derive the expression for the absolute error. They may ask you to find the expression for the absolute error, ask you to find the relative error, and also percentage error. In addition, that's what we're dealing with. In subtraction, we're going to look at that, multiplication and division. So, which formula, if I know that my exact value is capital X and my exact value of Y is capital Y. Then because maybe X is too long, maybe it is 2.333, it is recurring, I decide to round off that figure, let's say to 2 dps, and I write it as another. This time we're using unknowns, so I write it as small x. Then even this one I said to round off and I write it as small y. Now, what if I decide to add these two values? If I'm adding, of course, I'm going to add, instead of adding capital X plus capital Y, the ones I've written as small x and small y, I'll instead add X plus Y. What error will be there? What error would arise from the fact that I've added approximated values instead of adding exact values? So that's what we're looking for. What would be the error in X plus Y? What error would arise by me approximating capital X plus capital Y by small x plus small y? I don't know whether you're trying to get that. For instance, I've measured length of something as maybe 2.678, something like that. But since it is too long, I round it off to 2.7, maybe something like that. Then I also measure the length of some other thing as, let's say 3.489, like that. Then I said round it off maybe to also 2 dps at 3.49, like that. Then maybe somewhere they want me to get the value of, if this is my x and this is my y, somewhere they want me to get the sum of the length. Since I'm not using this, I'm using the approximated values. I'm going to add approximate value to the approximate value. Which error will come up? Which error will arise from the sum of these two? Sum of, by me summing up approximated value instead of exact values, which error will be there? This time we're not looking for the error, we're looking for the expression that we can use to find the error. Of course, we know how to find these errors from the work we've covered before. We looked at how to find the error bound in addition, error bound in subtraction, error bound in division, error bound in multiplication. We've done those things before. But now here we're dealing with unknowns. We're deriving the formula. We're deriving the different expressions that can be used to find the error in addition. Now here we're saying that the formula, if you want to find the error in addition, like in this case, I'll simply get the error made in X by me rounding off, writing capital X as small x. Which error did I make? So I get this error. So I'll get this error in X. I also get the error in Y by me writing capital Y as small x, as small y, I mean. Capital Y as small y. Which error have I made here? So to get the error in the sum of X plus Y, I'll simply add up the errors. The error made in X plus the error made in Y. That's what what we're looking at here. That's what we're looking at here. Then we went ahead and said, if you want to get the maximum absolute error, you simply get the absolute error in X plus absolute error in Y. Is it clear now for some of those asking for the explanation of the conclusion? Is it okay? Can we please, if you're not comfortable with this, you ask, because we're going to look at the same concept in addition, in subtraction, in multiplication. So just in case if you're not comfortable with this, you can ask. I give it more time so that we don't again waste a lot of time on the coming derivations. Are we comfortable with this?
No.
No. So what are we looking at here altogether? We're saying you're going to measure values. You're going to be having values. Let's say they'll give you, you have a value, let's say capital X. Maybe this capital X is too long and you round it off, you approximate it. And by you approximating it, you write it as small x. Let's say something like that. Maybe it is 3.333, you round it off and write it as 3.3. So capital X is representing the exact value, small x is representing the approximated value. So by you doing this, writing capital X as small x, you're making an error in it. And we're calling that error dx. We're referring it to that error as dx. Then maybe you also have another value, capital Y. This capital Y, maybe it's also too long and you round it off, you write it as small y. Maybe you have 5.77, maybe something, you round it off and approximate it. We looked at those things. By you rounding off, you're creating an error. So that's the introduction. We looked at rounding errors. or truncation errors. You can approximate by rounding off or truncating. So by you writing capital Y as small y, you made an error, let's say dy. That's the error in it. Now, later on, maybe they're asking you, like maybe you're doing experiment in physics. They say, write the value of x, write the value of y. Then tabulate your results, including the values of x plus y. But your x has an error, your y has an error. So even x plus y will have an error in it. That's the error we're looking for. We're looking for the expression that you use to find the error in x plus y. So what do we do? You simply let z be the same as my capital X plus capital Y. That's what I'm doing. But then we know that for me to find error, this is how we define the error. An error is the same as exact value minus the approximated value. So if I want to find my exact value, make it the subject to be the same as this plus that. That's what we're doing. So even y, exact value of y will be the same as approximate value plus the error made in y. Then even z that I've introduced, my exact z will be the same as approximate value of z plus the error made in z. But also here, exact values of z will be the same as exact value of x plus the exact value of y. Then approximate value of z will be the same as approximate value of x plus approximate value of y, like that. So here, I'm looking for the error made in this sum. And that error is represented by the x, because the z is representing x plus y. So the z represents the error made in x plus y. So I come here and substitute where there's capital Z, I put there approximate value of z plus the error made in z equals to approximate value of x plus the error made in x plus approximate value of y plus the error made in y. That's what I have. So at this point, I'll collect like terms, of course, write errors alone and write approximate values alone, and end up with error in z, z plus error in z equals to x plus y, which are the approximate values, plus the x plus the y. Then at this point, I can take this z this side. I'll end up with error in z being equivalent to x plus y minus z has cross equal signs, plus error made in x plus error made in y. This is what we're deriving. Now this point z, small z is the same as small x plus small y. That's how we define it. So that means that this and this will cancel. We shall end up with error in z equals to error in x plus error in y. What is the error in z? Error in z is error in x plus y. So that means that if I decide to write capital X as small x and I make an error dx, then I also write capital Y as small y and I make the error dy. If they want me to find the error in x plus y, it will be the same as the error in x plus the error in y. That's what we do. But then we define terms at the beginning of this lesson, and we talked about the term absolute error. How did we define absolute error? We said absolute error is the magnitude of the error. So let's introduce magnitude here, because there's a possibility that this error can be negative. So how do I get the absolute error? Absolute error in z modulus will be equals to error in x plus error in y modulus. But sometimes you're interested in the maximum absolute error. Maximum absolute error. I showed you up there using the other argument of 2 and 4 that the error in x plus the error in y can be at most, is always equal to or less than error in x plus error in y. So this is the maximum possible value ever of this absolute error here, x plus y modulus. So that means that our error in z, which is error in x plus y modulus, can be equal to or less than that. So they can ask you to find the maximum, derive the expression for the maximum absolute error in x plus y. This will be the expression for it. So this conclusion now holds. We say the maximum absolute error in approximating capital X plus capital Y with this is that and that. Hope you've now understood it.
Yes.
Okay. Now let's proceed. Let's move on to another term. We found the maximum absolute error. What's the maximum relative error? Relative error. Let me ask you to find the relative error. How do we find that? So how do we find the relative error? How did we define relative error? Can somebody tell us the definition of relative error? We looked at these things, so we should not. How did you define relative error?
The ratio of the absolute error to the exact value.
Yeah, the ratio of the absolute error. Relative error is the ratio of the absolute error to either the exact value. We said either the exact or absolute error over the approximate, like that, approximate value. We looked at this, and I remember we demonstrated it with 2 examples, which gave us almost the same result, absolute error, approximate value. Now, in this case, since we have our maximum possible, we have the maximum possible absolute error, we can also find the maximum relative error. And here, of course, our relative error will be equivalent to, we can say, maximum absolute error divided by either the exact value, and this will be equivalent to dz, which is our error, divided by, if we're dividing by the exact value, we shall divide by capital Z like this, modulus. It will be less or equal to error in X modulus plus error in Y modulus divided by Z, like that. But what's our Z? Our Z is capital X plus capital Y. And this will be the same as, we can write here, see less or equal to, this will be capital X, the X modulus plus the Y modulus divided by X plus Y. Like that. That is our relative error. Or that's if we've used the exact value. Or we can say our absolute error, relative error, will be the same as maximum absolute error divided by the approximate value. Approximate value, which will be the same as dz out of our approximate value is small z modulus, which will be less or equal to error in X modulus plus error in Y modulus divided by X plus Y, like that. So in this case, we have our relative error. That's how we find it. We say relative error can be absolute error divided by the exact value, or absolute error divided by the approximate value. And here we have it. That is it. Sometimes, of course, in some questions, they go ahead and separate this. They can also say is error in X out of X plus Y modulus. This is the same thing. They are simply changing it. So in most cases, they'll ask you to derive. For those of you with question banks, you can have time and peruse through. Check 2016, I think number 13, and number 14, 2013, number 13. There are these derivations. So sometimes they can say, write your error as this. So when you reach here, just separate it and write it the way they want it to be presented. So X plus Y, like that. This is also allowed. Even here, you can also separate and say it is error in X out of X plus Y modulus plus error in Y out of X plus Y modulus. This is also fine. That is our relative error, maximum relative error. So therefore, you can also conclude and say the maximum the maximum relative error in approximating capital X plus capital Y with small x small x plus small y is, you can write either the first one, error in x out of x plus y modulus plus error in y out of x plus y modulus, or you can write the other one, error in x out of, depending on what the question will present. Some questions it will be small values, so you write using, some questions will be out of exact values, you divide with exact value. If it is with small, you write with small, approximate, I mean, out of x plus y. Do you have any questions in that at this stage? Any questions here before we proceed? Hello? Do you have some questions at this stage before we proceed? Okwago. Is this step okay? Okwago Bernard?
Yes, teacher.
Yeah, because this work is coherent. We shall keep on building on what we learned like that. We're moving from simple to complex. So make sure you understand. You've also reviewed the work, but when you're going for another lesson, you must have reviewed the work we looked at before. Otherwise, this looks a bit strange. I'm sure it may be looking strange to some of you who have not looked at the previous work. I shared the first video where we defined all these terms. It is on my YouTube channel. Keep checking out on those videos and you review the work before the lesson. Okay, now the next term is percentage error. Percentage error. How did we define percentage error? Nathan, how did you define percentage error? Yes? We are listening, Nathan. Nathan, we can't hear you. Sorry? Okay, let's have Paul. Paul, what is percentage error?
The percentage error is the product of the relative error and 100%.
100%. So percentage error is simply relative error expressed as a percentage. Percentage error is the same as relative error, but expressed as a percentage like that. So when you write percentage error, write relative error as a percentage, it gives you relative error. So this will be the same as bx, maybe out of x plus y modulus plus dy out of x plus y modulus. All of these times 100% gives us percentage error. Or you can say it is the x out of x plus y modulus plus dy out of x plus y modulus. All of this, if you multiply by 100%, it gives us percentage error. So either way, here you have percentage error. And that's how you find percentage error. Percentage error is the same as relative error expressed as a percentage. We had those terms before and we had several examples about them. So I believe they are not a challenge. They're not a problem for you. I think that is understood. That's how we find percentage error. Then the other thing is you must know how to navigate through these expressions. They can give you, in a question, they can give you percentage error and ask you to find the expression for absolute error. If I have percentage error and I want to work it backwards to relative error, I simply divide this by 100. It will take me back to relative error. If I want to take relative error back to absolute error, I simply multiply by the exact value. Since for me to get absolute error, for me to get relative error from absolute error, I divided by the exact value or the approximate value. Now to move backwards, I have to multiply. The inverse of division is multiplication. So I multiply and I go backwards. For instance, if I divide this by 100, it gives me this. When I multiply this by x plus y, it takes me back to the absolute error. So you have, that's also what you should master here. So that's all about addition. In addition, they'll ask you, because in introduction we said, they'll ask you to find the absolute error, they ask you to find relative error, they ask you to find percentage error. We found all those ones for addition. We found the absolute error, the maximum absolute error, we found the maximum relative error, and we found the maximum percentage error. When they ask you to derive, they'll ask you to derive all those three in most cases. In addition, we're done with addition. Now let's go to subtraction. When you're subtracting, what do you do to find all these things? To find the absolute error, to find the relative error, and all that. So if you've understood addition very well, then subtraction won't be a challenge. If you understood subtraction. Subtracting. So if you're subtracting, how do you find the absolute error, the maximum absolute error? How do you find relative error? How do you find percentage error? How do you find yes, those ones, percentage error, relative error, and absolute error. Those ones there. So in subtraction, that means that we're dealing with x minus y. We're dealing with x minus y. So how do we start? We're going to have the same introduction, like the one we had in in addition. The same introduction will work. You have capital X, you have capital Y. You decide to, instead of writing capital X minus capital Y, you write small x minus small y. What error will arise from there? What will be the maximum absolute error that will arise from you? Instead of writing capital X minus capital Y, you instead write small x minus small y. What will be the absolute error in that? What will be the relative error in that? What will be the percentage error in that? Those are the three questions that you need to answer there. So let's start. Just like we did with the previous one, we shall say let me use this. Hope you're all comfortable with the color. If you're not seeing well, we can change it. So you can start by saying let capital Z be equivalent to, hello, mute yourself if you have noise in the background. Capital Z be the same as capital X minus capital Y. The exact value in the difference, let it be Z. Then the approximate value, of course, when you decide to, instead of writing capital X minus capital Y, you write small x minus small y, you'll end up with a small one with the approximate value as this. That's what we have. So here we're dealing with sets of values. I'll repeat this. We have exact values. We have a set of exact values. And those are capital X, capital Y, and capital Z. Then you also have a set of approximate values. A set of approximate values. That is set of approximate, which is small x, small y, and small z. Then you have corresponding errors in them. The errors in each of the terms that you're dealing with. We have the x, that's the error in x, the y, the error in y, and the z, the error in z. Of course, when I want to find the exact value of x, this will be the same as approximate value plus the error made in x. Exact value of y will be the same as approximate value plus the error made in y. Then the exact value of z will be the same as approximate value plus error made in z, like that. So that's what we have. Somebody has a comment in the chat. Color red is clear. Okay. So somebody says red is clear. Let me change to red and see. Now this is what we have. Now we go ahead and where there is exact value, we substitute their approximate values. Where we have exact, we put their approximate values. My exact z is the same as approximate value of z plus the error made in z, like that. Equals to approximate value of x plus the error made in x, like this. Minus approximate value of y plus the error made in y, like this. But now to shield this from this negative, I can put a bracket here to make sure this is one thing. And this is also, okay, I can leave that one. So my error, my z plus the error made in z, the next thing is I'm going to collect like the x minus y. That will be equals x minus y plus error in x minus error in y. Somebody is saying something. So somebody says, I restart the subtraction, the network was disturbing. Make sure you get stable network because we shall now not keep repeating. So subtraction, somebody says I repeat because the network wasn't stable. Subtraction, you have your exact values of x and y. But instead, you write small x minus small y, you subtract approximate values. I've explained that before. Somebody is saying something again. Somebody is saying I return to blue. Why are you tossing me up and down? Somebody said blue is not clear, I go to red. I'm in red, somebody says I go to blue. Okay, now okay, let's go back to blue. I have x minus y. These are the approximate values. Okay, these are my exact values, x and y. But instead of writing, subtracting x and y, I instead subtract the approximate values of x and y. Let's say you have 2.67777, but you don't have time for writing all that. Instead, write 2.68. Then maybe you are subtracting 1.666. Instead of writing that, you represent 1.7. We're not subtracting exact values, we're subtracting approximate values. And in that case, we have errors that arise. What would be the error? What error would arise from me subtracting approximate values instead of exact values? That's what we're looking for. What would be the maximum absolute error in that? What would be the relative error in that? What would be the percentage error in that? That's what we're looking for. Now, we have our exact values, a set of exact values, x plus y, I mean x, y, z. I have approximate values, x, y, z. Then you have the corresponding errors, this and that. Then we know this, we already did it, and in addition, that's why I was telling you this work is coherent. What we did the other side is still what we're going to start with this side. So we have capital X the same as that, capital Y the same as this, and capital Z is the same as that. So where there is capital, where we have exact values, we are removing them and we put approximate values. Somebody raise a hand. Angris, can you ask the question?
Since we're dealing with subtraction, I'm wondering why you are adding x, the exact values, why you're making them to be like added, yet we're dealing with subtraction. Can't it be x equals to x, small x minus dx?
Okay, thank you for that question. How are we getting this? We're getting this from the definition, of error that we looked at first. Definition of an error. We said for you to get an error dx will be the same as the exact value minus the approximate value. That's the error in x. So if I make the exact value the subject, we shall end up with this. If I want the exact value in y, we shall end up with that. Exact value in z will be the same as that. We've not reached here yet. We're still defining our symbol that we're going to use in the derivation. Is that okay now?
Yes.
Yeah, okay. So we have substituted them here. Now the next thing is I'm going to subtract the z on both sides, since I'm interested in finding the error in z, and our z is the same as x minus y. So we're finding the error in x minus y. So the error in x minus y, which is the error in z, will be the same as x minus y. Then I will subtract this z minus z, then plus error in x minus error in y, like that. What is this z? This z is the same as x minus y. So I can say I'm having error in z being the same as x minus y, which is the same as z, minus this z, then plus error in x minus error in y, like that. That's what I'm dealing with. So this and this will cancel. We shall end up with error in z being the same as error in x minus error in y. That means that when I'm subtracting two terms and I want to find the error, I'll simply subtract the errors, also the corresponding errors. If I'm getting x minus y and I want to find the error will be error in x minus error in y. That's what this formula is telling us. But then we're dealing with, in most cases, we shall be dealing with absolute error. Most of the questions will be asking me to find absolute error. So how do I find absolute error? Absolute error, I introduce the modulus. I explained this at that time, so I may not again spend a lot of time on it, like this. But remember, this one can also be written as, error in x plus negative error in y. These two are the same. If we know, these two are the same. I will not change anything. This is the same. Yes. Somebody is saying, do you need to present all this? Yes, you need to present all this while deriving it. You need to present it on the paper. But of course, as we practice, I'll show you some of the things that you may leave out. But as we're learning, we need to learn everything. When we're practicing, I'll show you some of the things that you can leave out and all that. But now that we're learning, we should learn everything from first principles. So this one can be written like that. But then in the previous derivation, when you're looking for the maximum absolute error, we said that the error in x plus error in y negative modulus, this is less or equal to the error in x plus the error in y, like that. But you know that modulus of a negative is always a positive. So this is less or equal to error in x modulus plus the error in y modulus. You can ignore the negative since you're applying modulus. So the maximum possible absolute error in subtraction is the same as the maximum absolute error in addition. This is what we ended up with in the previous derivation. You can see it here. Absolute error in addition, we ended up with this, which is the same as what we're getting here. And I remember when you're dealing with error bound, when you're dealing with actual values, we also came up with such a conclusion. We found the error in addition and found the error in subtraction and realized that the errors were the same. So even in the expressions we're deriving, they're showing us the same thing. The error in addition, maximum absolute error in addition, is the same as the maximum absolute error in subtraction. The expressions are showing that. So you may be asked to find this. And like I said, the most important part of this derivation is here, while introducing the modulus. Some of your colleagues, when they reach here, they just jump straight for the final expression. You'll have lost some marks in between here. You must show all these steps. How are you changing from the modulus on both to modulus on each? And you can't write equal signs. When you write equal signs, you've introduced modulus on individual errors, and you have equal signs here. That would be wrong, you know. This we must write less or equal to, because I showed you that using the 2 and 4. 2 plus 4 modulus. This will be the same as 2 modulus plus 4 modulus, yes. But when I have negative 2 plus 4 modulus, this will give me 2, but this negative 2 modulus plus 4 modulus gives me 6. So that shows that if you have a plus b modulus, this is sometimes equals to, like you see in the first case, or less than A modulus plus B modulus. That's what we looked at. So always when you reach here, this symbol is what they look out for. Make sure you present the right symbol. There is somebody mowing. I don't know whether you're still hearing me. There's noise outside. Okay, next term is how do you find relative error in subtraction? Let's be very fast. Relative error. How do I find relative error? We define relative error as absolute error over either the exact value or absolute error over the approximate value. The approximate value. So let's see. My relative error will be the same as what is my error in Z? Error in Z out of, if I use the exact value, it should be out of capital Z. And we know that this already is less or equal to, we found it here, it is less or equal to error in X modulus plus error in Y modulus divided by capital Z, like that. This will be the same as what is my capital Z? My capital Z is the same as capital X minus capital Y. My exact value of Z is the same as exact value of X minus exact value of Y. So this becomes error in X modulus plus error in Y modulus divided by X minus Y, like that. Or we say this can also be the same as error in X out of X minus Y modulus plus error in X, error in Y out of X minus Y modulus. We do this to avoid any chances of negative arising up because our relative error, absolute error, all must be positive. So in this case, if X is smaller than Y, you'll notice that we may end up with a negative value, which you don't want. That's why we separate and write the modulus in video terms, that we end up with a positive relative error. Then percentage error, percentage, Daniel, you raised your hand, what is it? Daniel? Your hand was up.
So why are we adding here?
Why are we?
Like adding on whatever absolute error instead of or whatever subtraction.
Yeah, were you following up this step? Did you understand this step very well? This one here.
Not really.
That one. We said, if I have 3 minus 2, I can write this as 3 plus negative 2. Do you agree with that?
Yes.
So even here we said error in X minus error in Y is equals to, we can write it as error in X plus negative error in Y, something like that. Then we went ahead and introduced modulus. We said, if you're looking for the maximum absolute error, then you must introduce this less or equal to sign, the utmost symbol. So we have error in this, error in X minus error in Y plus negative error in Y. This can also be written like that. Hope you agree with this. Which introduces the plus. The plus is coming in at this point here. We're not introducing it from down this way. We're introducing it from this side. That's why the negative disappeared. This is where the negative disappeared and introduced a positive. So and that's why we're adding this side. Hope you understand it now. You know where the plus is coming from. Mayanja?
Yes.
Yeah, do you know where the plus is coming from now?
Yes.
Yeah. So we're deriving it. When you're looking for the maximum absolute error, the modulus has to be on individual terms. But before we introduce it, we must separate it and attach the negative to only the last term, which is negative dy. It becomes negative dy. And then, so that when you introduce modulus, the negative goes away. And we end up with the maximum absolute error in subtraction. That would be it. Then relative error we divide by the exact value or the approximate value. You can say, or relative error, somebody said we go back to blue, relative error will be equivalent to error in Z out of approximate value in this case, which will be less or equal to error in X. We know why it is coming in, why it is a plus now, error in Y, divided by this time small z, which is X minus Y. And this can also be written as error in X out of X minus Y modulus plus error in Y out of X minus Y modulus, like that. And lastly, when they ask you to find percentage error, our percentage error will be equivalent to we define percentage error as we defined it as when you express relative error as a percentage error equals that times 100. So that means that our percentage error will be the same as relative error times 100%, which will be the same as, of course, our relative error is this out of that. So this times 100%, which will be less or equal to error in X out of X minus Y modulus plus error in Y out of X minus Y modulus, like this. The whole of this times 100%. This gives us the percentage error in subtraction. That's how you find it. Or you can also use, or you can say it is error in X out of X minus Y, use exact values, plus error in Y out of X minus Y modulus all of these times 100%. So you notice that relative error in addition is not the same as relative error in subtraction, but absolute error in addition is the same as absolute error in subtraction. The two are the same. Absolute errors are the same, but relative errors are different. We have some questions here before we add on another one. Like I said, this section, we are looking for the expressions of errors: absolute error, percentage error, relative error in addition, subtraction, and subtraction, multiplication, and division. We've done so far two, addition and subtraction. Do you have any questions on the two before we proceed? Any questions from this before we proceed? So we can say the maximum percentage error in approximating X plus Y with X, not plus, we're dealing with minus. X minus Y with X minus Y, where these are exact values and these are approximate values, is ln X out of X minus Y modulus plus ln Y out of X minus Y modulus times 100%. They'll ask you to carry out this derivation. They will say, maybe X was measured with some error in it and Y was measured with some error in it. Derive the expression for the percentage error, or show that the percentage error in X minus Y is this. They'll ask you to carry out those derivations for around 6 marks. And after that, they say, they give you some values and ask you to find the percentage error. Now here, the marking points, I've tried to emphasize the marking points. When you're introducing less or equal to sign, like here, this point, you have to be very careful while separating this and introducing the less or equal sign. That's the only point that you need to be careful with. Even in addition, the same point, you have to be careful with it. At this point, when you're introducing modulus, first introduce modulus on both, then introduce modulus on simple term, on each term. And as you introduce modulus on each term, make sure you introduce also less or equal to sign. If you leave it out, those marks will be lost. Those are the marking points. Are we together there? Should we proceed now? Should we proceed? Let me see. Ezra, are you comfortable with what we've covered so far?
Yes, teacher.
Okay. Let's now move on to multiplication. Multiplication. These are now, multiplication is the most common. Multiplication and the division are the most common. Multiplication. Multiplication. Change this to ink, to text. This now when you're dealing with capital X and Y. Yeah, you measured somebody, maybe you measured, in this case, you measured the length of, let's say you have a rectangle. Let me get my pen. Blue is fine. Ink to shape. You have a rectangle like this. Oh, whatever, rectangle like that. Now, this rectangle, you measure the length as, let's say, X. The length of the true length of this rectangle is supposed to be capital X. And the true length is supposed to be, the true width is supposed to be capital Y. But then, for you, maybe you approximate the length because he has maybe very many decimals. You write the length as small x and small y, like that. What error will you make in the area? What error will you make in the area of this rectangle due to these approximations? What error will you make in that area? Of course, we looked at errors in multiplication, error bound in multiplication, where you said when you, for you find the error bound in multiplication, you'll find the maximum value, get the minimum value, subtract and divide by 2, or get the working value, get the minimum value, subtract, or get the maximum value, and subtract the working value from it to get the error. We've looked at that already when you have the values. When, for instance, they said the length here is 3.14, and maybe here it is 2.67, then maybe you approximated it as 3.1, and here 3.6. What error did you make? We simply look for the maximum value, maybe like that. We know that approach. But now in today's lesson, we're not interested in the error, but we're interested in the formula, in the expression that you can use to find the error in multiplication. Which expression can you use to find the error in division? Which expression can you use to find the error in division without having to use the other approach of minimizing and maximizing? Without you going through the approach of maximizing and minimizing. My one note has gone away, let me get it. So that's what we want to, that's what we're looking at today. How can you derive the expression? Which expression will I use to find the maximum absolute error? Oh. So this is what we do. Still what we did the other side is what we're going, the way we introduced our work, the other side is how we're going to introduce it here. We shall say, let me get a pen. I'm winding up with this multiplication, that the next lesson look at division, and we'll look at division. I'm just going to give you a hint on how we do this, then the next lesson we shall do it seriously. Because our time is almost up, and I know some of you have lessons after this. I don't want to keep you in class for long. So you'll say let, just like the way we said the other one, let Z, it can be any other letter. And here we're using X and Y, they can say A and B. So make sure you don't again cram that it has always be X and Y, Z and all that. Then you can use other letters. So be flexible. This will be the same as, let it be the same as that. When my capital Z is the same as this, my small z will be equivalent to small x times small y, like that. So we also know the other things. We know that our capital Z is the same as the approximate Z plus the error made in Z. This we know. Then our capital X is the same as approximate value of X plus the error made. By you writing this length as small x, which error did you make? You know, something like that. So my capital Y is the same as Y plus the error made in Y, like this. Now from this, we are going to substitute in this. We substitute, eliminate the exact values and substitute the approximate values. So we shall have Z plus error in Z equals to X plus error in X. This is a bracket. This is standing for capital X. Then also Y plus error made in Y, like that. Then from here, I go ahead and expand these two brackets. I'll end up with Z plus error in Z equals to xy plus x error in y plus y error in x plus error in x error in y. Now here at this point, also bring in another important argument. Error in x and error in y. How do we get rid of them? Now here we shall say that let me just give you another example, a simple example here before we proceed. If x is 2.1 and maybe my y is 3.46, what is the maximum error that can be made in x? Error in x will be the same as, okay, let me use the symbol that we're using. Error in x will be the same as a half times 10 power negative 1. This gives me 0.05. My error in y, just if you're dealing with exact values like we did, when you've been given values like we did in the previous section of this topic, this will be the same as a half times 10 power negative 2, which gives me 0.005. Now, when you have this, now here when you're expanding, let's now use this expansion here. When I'm expanding x plus dx into x into y plus dy, somewhere I'll have x times y, which will be this times that. Then somewhere I have x plus error in y, which will be this, which will be this times this, then plus y times error in y, then plus error in x, error in y. Can somebody get for me this product? Let's somebody the calculator get for me x times y, 2.1 times 3.46. What do you get? Let's compute this very fast. I want to use it just to explain something here. Somebody with a calculator, give me these answers. X times y, what does it give you? X times the, let people compute different parts so that we just end up, we save time. Get me this, x times y, what does it give? We have around 7 minutes at the end of this lesson, so let's not waste a lot of time. X times y.
7.266.
7.26. You give me everything that you see. 7.266 plus what is x plus dy? X times dy, I mean 0. X is here, dy is here. What do you get? What do you get?
0.0105.
1005, eh? Okay.
No, it's 10 then 5.
Okay, this one not there. Then plus, what is this one? We're having 3.46 times 0.05. Gives us
0.0173.
73. Then lastly, get me this other one, 0.0105. 0, 0. Another 0, I think. Yes, Mutumba.
Nothing.
Don't have a calculator. Okay, so what's the calculator there? Give us this.
0.0
25 like that. Now, when you look at all these answers, now let somebody add this. When you add this, add for us these first 3 only and tell us the answer. Add for us the first 3. What do you get?
7.2938.
2938. And then add 0.005 on that answer, 0.0025. Add this one. What do you get? 7.29.
405.
405. Now I want us to look at these 2 expressions. I mean these 2 answers. You notice that this value here is very, very small. It is the smallest of the values we have. It is the smallest of the values we have here. We have this is 7, this is 0.01, this is 0.01, but this is 0.000025. So it is very small. It is a very small value. You get it? It is a product of errors, so it is very, very small. Now here, we have to ignore it. We leave it out. Why? Because even if you don't add it here, it doesn't create a very big difference. This is 7.2938. If I round off, it also gives me 0.294. Here, it is the same thing. Even after adding this, it's almost the same thing. So it's a negligible value. It is ignorable. We can leave it out. But we don't just leave it out there. We must give a justification. We must give a reason why we're leaving it out. So the reason that is acceptable here in this derivation is this one. You say error in X is very, very small, is far way less than, this is the symbol we use, far way less than X. Then the error in Y is also far way less than Y. And what is the result after this? For them being so small like this, the result will be when you get the product of them, error in X times error in Y, it will be approximately equals to 0. It is ignorable. This is the reason you give. And this is a marking point in this derivation. You leave out that step, the marking stops there. You know, when you leave out that step, the marking stops there. So anything written beyond that will be null and void. So I just gave you all this to make sure I come at this point here. Why do we ignore this? We ignore this product of small values. We ignore this because it's a product of small values. Which value is negligible. It is very small. It doesn't change so much even if you don't add it to this. It doesn't affect the result so much. So this is the reason you always have to give when you reach this point. The product of small values is very small. You said the X is far way less than X. We use double of them, less than. Even the Y is far way less than Y. So as a result, the product of the two is almost equals to 0, is approximately 0. So that means that next step, I don't know whether you've understood this, can maybe somebody, because it's an important step in this derivation. Have you understood that step? Dennis?
Yes.
Okay. All right, so let's now proceed. We shall say error in Z plus, Z plus error in Z will be the same as xy plus x dy plus y dx, like this. Then the next step is we subtract Z on both sides. So we shall have error in Z being equivalent to xy minus Z plus x dy plus y dx, like this, y dx like that. So this Z, remember while defining, we also define small z. We say if capital Z is capital X plus capital times capital Y, then small z will be small x times small y, like that. So here we end up with this and this will cancel because they're the same. So error in z will be equivalent to x, error in y, plus y, error in x. This is the error. But always we're interested in the absolute error. What will be the absolute error? Absolute error, we introduce the modulus. So it is x error in y error in x. They swap. The approximate value of x goes with the error in y. So my absolute error modulus will be equivalent to, I first introduce modulus on both. This step, I think we're now getting used to it, like that. That is the absolute error in Z. Then if it is maximum absolute error, then we shall have error in Z modulus. Not yet. Not this one. I first select the two. I'll say x error in y plus y error in x modulus is less or equal to x error in y modulus, I think we now know this, plus y error in x modulus, like that. That is my maximum absolute error. So therefore, error in Z, this will be less or equal to x error in y modulus plus y error in x modulus, like this. And here we can now conclude and say the maximum, and this question is very popular, maximum absolute error in approximating capital X, capital Y with small x, small y is error in x, that's this one, plus y, error in x, like that one. So I simply get, if they say, if let's say the area, the approximate value here is 2.4, maybe 3, 2 maybe 4 points. This is 1.67, and want me to find the error made in the area due to the approximation of the length and width. I'll simply say 2.4 times the error made in y, which will be a half times 10 power negative 2, then plus 4.6, 1.67 times the error made in the length, which will be a half times 10 power negative 1. And that gives me the error made in the area due to the error made in the length and width. That's how we find it. So even the other work that we've been looking at, where they say x equals to 2.4 and y equals to 3.6, maybe 7. These values have been rounded off. Find the error in xy. Remember, we looked at the method of finding the error in xy, where we said you can find the minimum value, find the maximum value, and after doing that, you go ahead and subtract them and divide by 2 to get the error. You can also use this method to come up with the same answer that we're using the other side. It is okay. That can be used. You can also use this other approach to find the limits. They can say find the limits within which the exact value of xy lies. Exact value of xy lies. I have x, I have y. I can find the working value from this by simply multiplying them. After getting the working value, I come here and find the absolute error, maximum absolute error. So my working value plus the maximum absolute error gives me the maximum value, which is the upper limit, if at all they want the limits. Then my working value minus the absolute error, maximum absolute error, which I can get from this, it gives me the minimum value. So I can write my range easily. We shall look at these practice questions after these derivations. That's when we shall go ahead and practice this. So lastly, as I wind up, they can ask you to find, from this they can ask you to find relative error. Relative error, of course, we know it is the same as absolute error divided by either approximate or exact value. But now since this one I have x here, which is my approximate value. I have y here, which is my approximate value. It is always okay for us to divide by only the approximate value. Why? Because we have approximate values here, so that they can cancel. But if you bring capital Y, there's no way capital Y will cancel with small y. They are not the same. So we shall say this, which is less or equal to x error in y divided by xy plus y error in x divided by xy, which are the approximate values. So this, you notice that x and x will cancel. Here y and y will cancel. So I'll end up with my error being equivalent error in y out of y modulus plus error in x out of x modulus. This is my relative error, percentage error. You multiply that by 100%. Yeah, so that's what we were supposed to look at today. In the next lesson, we can't rush. We shall look at them slowly. And of course, when you finish up the division in the next lesson, we shall have covered 90% of error analysis. So then the other part will be the other 2 lessons. Shall add extra 2 lessons for simple revision of doing the enable questions, standard questions from question banks and all that. Yeah, and the thing will be very easy. Any questions, any opinions, any inputs, any observation? Hello, I'm stopping the screen share. This is what we've looked at. It is 10:47, so we've even gone beyond, since we started late, we've gone beyond with some minutes. Yes. Okay, so any questions then? Are you comfortable with what we looked at today, much as you came in a bit late?
Yes, sir.
Okay, and then you'll find this video on YouTube. Let me stop the recording.